Blood is the storyteller of every crime scene. Silent, honest, and impossible to bribe. Every bloodstain holds a moment frozen in time. Decoding it is like reading the victim's final words. In forensics, we don't follow the oral evidence. We follow the blood drops. They lead us straight to the truth. No bribes, no lies, just stains that speak. This is your channel where science meets investigation and every clue tells a story. If you are fascinated about forensic science, crime scene analysis, and discovering the untold truths hidden behind the evidence, you have just found your perfect place. Join me on this journey as we uncover the truth one clue at a time. What is bloodstain pattern analysis? Bloodstain pattern analysis is the study of how blood behaves when it hits a surface. By examining the size, shape, and distribution of stains, forensic experts can determine how, where, and when a violent event took place. But how exactly does this work? Let us break it down. Types of bloodstain patterns. One is passive stains. These stains form naturally due to gravity. Think of blood dripping, pooling, or flowing from a wound. For example, if a person with a deep cut walk through a room, they may leave a tail of droplets behind. They are round in shapes. Subtypes. Drip stains. Individual blood drops that fall straight down. Pooling stains. Large collection of blood that indicate a victim stayed in one place. Flow pattern. Blood that moves along a surface due to gravity, often following the contours of an object of a body. Transfer of stains. This is also very important in blood pattern analysis. These occur when blood-covered object touches another surface, leaving a print or smear. For example, a bloody hand leaving a print on doorknob or a fabric pattern appearing in a stain. In these subtypes, wipe stains. When something moves through an existing bloodstain, smudging it. Swipe stains. A blood-covered object brushing against a clean surface, leaving a streak. Contact transfers. Clear prints like shoe impressions or fingerprints in blood. Projected stains. These results from external force acting on the blood, creating distinctive patterns such as spurs or sprays. For example, a gunshot wound often produces a fine mist due to a high velocity of blood being expelled. In these subtypes, arterial spurts, blood gushing in pulses due to cut artery, often forming an arc-like pattern. Impact spatters, blood breaking into droplets when struck by an external force. Low velocity spatter, large droplets, more than 4 mm size from slow impacts like blunt force trauma. Medium velocity spatter, smaller droplets 1 to 4 millimeters, seen in stabbing or beating. High velocity spatter, a fine mist less than 1 millimeter produced by gunshots or explosions in high velocity spatters. Cast off patterns. Blood flung from a moving object, such as a bat or knife, leaving linear blood spatter pattern or stains on nearby surfaces like on walls and ceilings. We'll see the shape of bloodstain when falls from different heights. First 1 feet, 2 feet, 3 feet, 4 feet, 6 feet. Like this, if height increases, the shape of bloodstain also increases. Key aspects of blood spatter analysis. Angle of impact. The shape of blood droplet changes depending on the angle at which it hits a surface. A perfectly round drop suggests a 90-degree impact, while an elongated stain indicates a sharper angle. Second one is point of origin. By analyzing the angles and trajectories of bloodstains, forensic experts use trigonometry to determine where the blood comes from. It helps to reconstructing the crime scene. Third one, velocity and weapon identification. Large, slow-moving droplets suggest blunt force trauma. Smaller, medium speed spatters are common in stabbings and beatings. A fine mist typically indicates a gunshot wound or explosion. By studying these patterns, forensic teams can estimate the number of blows, determine the victim's position, and even validate or challenge witness statements. By examining the edge of dried stains, this is called skeletonization. Forensic experts can estimate the timeline of events, helping to confirm or contradict alibis. Now we'll discuss one case study. A man was found dead at the bottom of a stairwell, suffering from severe head injuries. His wife claimed he had tripped and fallen, but when forensic experts analyzed the bloodstains, they uncovered a different story. Key findings. The blood patterns showed multiple points of impact, unlikely in a simple fall. Cast of stains on the walls and ceilings suggest a weapon had been swung repeatedly. A wide pattern near the landing hinted that something or someone had blocked the blood from reaching that area. A drip trail led away from the scene, indicating movement after the initial injury, suggesting an attempt to stage the scene. Further testing found traces of the victim's blood on the wife's shoes. Confirmed with the evidence, she confessed. An argument had escalated into violence in this case. Thanks of blood spatter analysis, investigators revealed the truth. This was no accident. Today, we learn how to determine the angle of impact, area of convergence, tangent of the angle of impact, and how to measure distance and determine the height of the source of blood spatter. First, we'll determine the area of convergence. This is the point where blood droplets originated in 2 dimensions on the floor 1, 2, 3, 4 and 5. Let us start by finding the area of convergence. Take each bloodstain and draw straight lines through the long axis of the elliptical stains. Expand these lines backward. They should all meet or get close to meeting at a common point on the floor. This intersection is the area of convergence. In our case, it is located here, as you can see in the diagram. (10°, 20°). Like this, if you increase the angle, here, by increasing the angle, you can see the droplets in oval shape. So these droplets can give angle of impact. By taking width and length of the droplets, we can calculate the angle of impact. This tells us how steep or shallow the blood droplet stuck on the surface. The more elliptical the stain, the smaller the angle. Use the formula angle of impact is equal to sine inverse width by length. For example, let us look at stain 1. Here its width is 4.5 millimeters and length is 9 millimeters. Divide width by length, that is equal to 0.5. Now take this inverse sine, that is sine inverse of 0.5, and you get approximately 30 degrees. Repeat this for each stain. Here are the results we got from our data. Stain 1, width 4 millimeters, length 9 millimeters, its value is 0.4444. 26 degrees. Similarly, stains 2, 29 degrees, 3, 28 degrees, stain 4, 30 degrees, and stain 5, 25 degrees. After calculating of all stains, we'll find the average angle of impact, which is about 27 degrees. Calculating the tangent of the angle of impact. Display, here you can see in this calculator, I'm showing the how to calculate tangent calculation. Now we calculate the tangent of each angle of impact. For stain 1, where the angle is 25 degrees, we'll find the tangent. Tan 25 degrees is equal to 0.4663. Here is the complete list from the data. For tangent of 26 degrees, 0.4877, 29 degrees, 0.5543, 28 degrees, 0.5317, 30 degrees, 0.5773, 25 degrees, 0.4663. Like this, we can calculate the tangent. Next, measuring the distance from the stain to the area of convergence. This is very, very important. Next, we need the distances from each stain to the area of convergence. For stain 1, the distance is 9 feet. For stain 2, it is 8.5 feet, and so on, averaging out to 8.78 feet. Determining the height of origin is very, very important. Here this triangle diagram showing that is the opposite side is height, adjacent side is distance, and angle that is showing. Finally, we'll use the formula. Height is equal to tangent of angle into distance. For stain 1, what is the tangent of angle? 0.4444 into 9 feet. That is equal to 3.9996. That is approximately 4 feet. Repeat this for all stains and get the heights. In this case, the heights calculated are given in this table. 4 feet, 4.71, 4.89, 4.85 and 4.10 feet. Taking the average, the height of origin is approximately 4.51 feet. So you have it. By using simple measurements, some trigonometry and a little detective work, we have reconstructed how and where this bloodshed event occurred. In all cases, I am using the same methods. Why blood spatter analysis matters helps reconstruct from crime scenes and timelines, identifies weapons, number of blows and victim, attackers, positioning, etc. Blood pattern analysis can support or contradict witness statements and suspect's alibi. It provides compelling scientific evidence in court. Challenges in blood spatter analysis. BPA subjectivity. Different experts might interpret patterns in different ways. Environmental factors, airflow, surface texture, and contamination can alter the blood patterns. BPA requires expertise. Proper analysis takes years of training and experience. Blood pattern analysis not always conclusive. Bloodstains alone don't always tell the full story. They need to be combined with other forensic evidence. Blood spatter analysis is not just about stains. It's about revealing the hidden truth behind every drop. Stay tuned for more insights in the world of forensic science. This is Sureshtaruvu, your forensic guru, signing off.